Good afternoon, innovators. Welcome back to the fourth edition of Epsilon, Synergy of Realities. I am Bobby Mehta, Technical Head at IEEE, and I am thrilled to see so many curious minds joining us today.
Hello visionaries, I am Shruti Rawat, Creative Head at IEEE SGST, and it's my absolute pleasure to welcome you to day 2 of the WI track, Building a Simple Spiking Neural Network. Today is not just about learning, it's about creating. Yesterday, we embarked on a fascinating journey into the future of computing with our WI session, Neurobytes, the next wave in computing. We sparked a fire of curiosity, and today, we fan those flames into action.
You are right, Shruti. Today, we are diving into machine intelligence by simulating how neurons fire and communicate with spiking neural networks, building the neurons of the future. And who better than to lead us on this thrilling journey?
Absolutely. It's an honor to introduce our speaker, Dr. Helena Bahrami, a leading expert in brain-inspired deep learning models with a focus on spiking neural networks.
Her groundbreaking research predicts neurodegenerative diseases using these models, alongside immersive 3D visualizations. As an industry leader in AI, she specializes in SNNs, generative AI, and machine vision systems.
She has taught at prestigious universities like AUT, that is Auckland University of Technology, and is known for her leadership in AI innovation.
So, without further ado, let's extend a hearty welcome to the trailblazing visionary, Dr. Helena Bahrami.
Dr. Bahrami, we are incredibly grateful to have you here today. Your expertise and insights will undoubtedly enrich our understanding of spiking neural network and their applications.
Thank you very much. Good afternoon, everybody, and I'm very honored to be in this session. Thank you for inviting me. Let's start an exciting journey to have a hands-on on implementing a spiking neural network, actually a simple network, but with all components. I'll start my presentation first by sharing my slides. In the second half of our presentation, we will move to Google Colab to see the implementation and explanation of code. And afterwards, we will wrap up with questions and answers. So let's start. Sparking neural networks, an overview of neuromorphic programming tools and frameworks. So today's presentation is about introducing different libraries of Python for implementing a Spark neural network, and also introducing the existing neuromorphic SDK and hardware, and also jumping into a kind of small implementation of spiking neural network to have some understanding and idea of how a learning algorithm can be implemented, trained, and observed visually.
Ma'am, your screen is not visible, I guess.
Oh. How about now?
Like you're sharing the PPT.
Can you? Yes, yes.
Ma'am, the PPT is not visible.
Okay, let's do it again. So can you see my slide now? Hello?
No, ma'am, not visible right now.
So I think that we need to give it a time. Can you see the slides, PowerPoint?
Yeah, ma'am, the screen is visible, but you have not
Okay.
opened in PPT.
I opened it, but I think that there must be some problem. Oh. Okay, let's start it again. How about now?
Yes, ma'am, it is visible now.
Okay. So sorry about the technical issue. So let's start again. As I mentioned, the title of this workshop today is Sparking Neural Networks, an overview of neuromorphic programming tools and frameworks. So we will start this journey by having an overview of neuromorphic programming tools and frameworks. I'll introduce Sparking Neural Network component, and I will briefly explain each component. And afterwards, we will look at the Python libraries available for simulating Sparking neural networks. And we will have a guide on simulating a simple Sparking neural network on Google Colab. And we will see implementation of neuromorphic algorithms such as Spike algorithms, and also Leaky Integrate-and-Fire neuron model. Also STDP, the synaptic plasticity, a kind of Hebbian learning. And we will have all those components together to build a simple network, and we will wrap up our session with Q&A. You can find the workshop on Google Colab. I provided the link, so if people want to access to this environment later on to study it in more detail, you can take a look at the code. So the neuromorphic computing is an emerging field. This field mimics architecture of human brain, leveraging the natural processing power of biological neurons and synapses. These systems are different from the traditional von Neumann architecture. In the von Neumann architecture, we have a shared memory buses to communicate with different component of the processing unit. And due to this setting, the data requires to communicate with different component, and it has a bottleneck for fast computing. Even though currently there are a lot of adaptation for parallel computing and using GPUs and very efficient hardware, still they are not energy efficient, and they are not as fast as we expect for having having it available for huge data, like streaming data, like IoT devices. But the neuromorphic hardware promise by focusing on low power and event-driven computation, a real-time processing for current application of IoTs, or providing some tools for researchers and neuroscientists to observe human brain. And there are a lot of capabilities that this new architecture brings, and there are new and powerful application that currently around the world people and researchers are working on. As I mentioned, this hardware is designed in a way primarily to help researchers to simulate sparking neural network. Sparking neural network are the third generation of artificial neural networks, and there are, in compared to the previous generation, there are biologically plausible and very similar to real biological brain in terms of its component and learning behavior. So the difference between the von Neumann architecture and neuromorphic computing, as I mentioned it before, is in the way that these two different architectures handle data. In the first architecture, we can see that the bus communicates between different components, CPU, ALU, and also there is a shared memory. But in the neuromorphic computing, we have different design for receiving address event-driven data, the data that are turned into zeros and ones and handled by kind of crossbar configuration, so that in parallel massively is available for a huge number of neurons. And because this architecture provides capability for biologically plausible learning, we can have thousands of synapses. Currently, the current architecture is limited with 256 synapses per neuron, but there is a promising hardware emerging in Sydney University that we can, in the next slide, look at that. So this is a visual kind of representation of both architecture. On the left hand, you can see von Neumann architecture. It is a normal architecture that the current computational system uses. And on the other hand, you can see neuromorphic architecture. Most of this neuromorphic hardware, they have built-in kind of learning mechanism like STDP. They have built-in neuron model. We will dive in different neuron model later on, and they are designed for using energy efficient and real-time computational process. As I mentioned, currently, actually, before 2024, these hardware were limited by having 2056 synaptic connection per neuron. But new hardware in a larger scale was designed and introduced by Western Sydney University, and it has 228 trillion synaptic operation, which is a massive and huge kind of advancement in this field. And they are going to make it available for researchers and developers. And this massive computer can be used in AI and robotics and biomedical field, and also help neuroscientists to understand the human brain activity. And you can see this is the huge infrastructure of that neuromorphic design that has a huge number of synapses ready for computational purposes. The neuromorphic frameworks have different kind of categories. We can see the most important one, NEST, which is a neural simulation tool. This is a large-scale sparking neural networks framework. This is a kind of framework for simulating a large scale sparking neural network, and it is optimized for high performance computing, the computation that uses cluster and parallel computation. The other framework that is well known and used in a lot of development by mostly a student and researcher is Brian. This framework is Python-based, and it is good for rapidly prototyping spiky neural networks, and it is flexible and have a good acceptable performance, not like Nest, but it is acceptable for a small scale research. The other framework that we have is Spinnaker. Spinnaker is a framework or SDK that is specific to Spinnaker neuromorphic hardware. It can simulate real-time large-scale spiky neural networks. And I can say that currently AWS uses Spinnaker to in parallel, use IoT processing in a real time, in a streaming fashion. The other framework is NanGo. This framework is building for both biological and artificial neuron models. So it can both support spiky neural network and traditional neural network. And it can support Lohi, which is a neuromorphic hardware. And also it can be used for a large scale spiky neural network simulation. We have Intel Lohi SDK as another type of frameworks. This framework is a neuromorphic framework that has a chip design for a spiky neural network. It comes with an API for developing and running on Lohi hardware, and it is supported by Intel. It is developed by Intel developers. We have another framework. I think that this framework is much more popular. This framework is Python-based API, and you can easily switch between different simulators without changing your code. It supports Nest and Brian, and also Neuron. So the power of this framework is that if you implement your code with no changes in your learning algorithm, you can simulate it on a hardware. The core capabilities of neuromorphic framework is that they are event-driven computation. It is very important for us. Currently, the current state-of-art hardware, they are very energy intensive, computational intensive, and they uses a lot of power for computational purposes. And you may have heard that the new AI model, like language model, large language model, they require a huge amount of energy. The event-driven computation makes this hardware much more energy efficient. Why? Because each neuron, they stimulate once they receive an event, so they don't process all the information. If there is an event in that kind of streaming data, they will propagate those information to other neurons that are connected to this specific stimulated neuron. And they have synaptic plasticity and learning. So this is very important because it is a kind of learning that captures temporality in the data, besides using information related to the topological connection between neuron in the architecture. Temporality is important because it is a biological phenomena in the brain. The brain learns based on the temporality and the frequency of occurring an information or an event. The most important or well-known algorithm is spiking spark time dependent plasticity. And also this hardware and framework, they support, some of them supports Hebbian learning, which is a traditional learning that we have currently used in networks like CNN, convolutional neural network, deep learning, or any machine learning neural network that they use a traditional way of handling analog signals. And also reinforcement learning. There are a lot of variety of reinforcement learning using reward and penalty to adjust the weights. Also, there are a variety of STDP that are compatible to use this specific learning mechanism. We will dive into the STDP, and so you understand what is the difference between STDP and reinforcement learning. And these neuromorphic frameworks, they are hardware compatible. Some of them are specifically designed for supporting a specific hardware, like a Spinnaker, like the NX SDK that supports Lohi, and also Ningo that supports Lohi. So they can also, like a framework like PyNN, that is much more a kind of unified framework and supports different kind of hardware. And also they are scalable. Scalability is important. If you are going to design a simple network for your research purpose, you can use this framework. Also, if you want to implement a huge infrastructure that can handle like thousands of IoT devices scattered all over the world, sending you information, you can use this hardware and this framework to help you to process those information. And also, the main purpose of this kind of framework is to help in neuroscience research. So for neuroscience research, if you want to implement a real scale like the size of brain with synaptic connection, as I mentioned in previous slides, we can imagine that the hardware requires a huge and like kind of a big hardware arrays for implementing neurons, billions of neurons, and 20,000 synaptic connection per neuron. And we saw that Southern Sydney University already designed such a huge supercomputer that is dedicated for sparking neural network and biomedical research. So let's look at this Python library for simulating sparking neural networks. As I mentioned before, we have Brian. It is popular, it is flexible, known for being user-friendly, and it is a Python-based simulator. So I think that most of people can easily use this specific framework for developing a simple sparking neural network. And it has a kind of customizable neuron model. It is important because you may not want to be limited with a certain neuron model. You want to have your own neuron model for your research purpose. And it has support for different learning algorithms. You can have a customized learning algorithm, or you can use the built-in learning algorithm that this framework supports. And as I mentioned, the use case is small to medium networks. It is suitable for research project or for educational purposes. NEST is a much more powerful simulator for large-scale sparking neural networks. And it is optimized for brain-like simulations, brain-like simulations is the variety of the computational model that they try to mimic brain behavior in terms of computation. It has event-driven features. It supports parallel computing, as we mentioned before. It supports HPC, high performance computing. And if you know, high performance computing use clusters of or node of cluster nodes in parallel to provide a big computational power. And it has a large library of neuron and synapse model. So it can help to develop a full-scale application, and it can be easily parallelized over clusters of node, and in a very quick and fast way, train the learning algorithm and use it for real-time application. There is another library, BindNet. It is a library on top of PyTorch. This library helps you to implement sparking neural networks, and also it provides you the capability to merge it or to develop a hybrid model with convolutional neural networks. It supports reinforcement learning, and as I mentioned before, because it provides some capability to combine it with a traditional convolutional neural network, it can have a better performance in compared to traditional sparking neural network. And we have PyNN. This is a kind of unified API for SNNs. So if you use this specific library without changing your code, you can reuse it across different framework like Nest, Neuron, and Brian 2. From the Nengo, we have a large-scale neuron model repository, and also it supports both a sparking and non-sparking network. And the hardware target for Nengo is Lohi, and it has features that supports biologically plausible and artificial models. Biologically plausible, when we say this model is biologically plausible, mostly we refer to the neuron models that are a kind of inspiration or mimicking real neuron behavior, and also the learning mechanism we refer to a spark time dependent plasticity. When we are talking about artificial models, there are all kind of traditional artificial models that are used in deep learning and convolutional neural networks. This framework can help to build cognitive modeling. Again, it is a kind of application in neuroscience to observe or research about human brain activity. It supports neuromorphic hardware, and it can help to build machine learning, not specifically the biologically plausible one like sparking neural network. You can use this framework to develop and use traditional neural networks. So we talked about framework and hardware that are provided to support brain-like computation or biologically plausible computation. When we refer to biologically plausible computation or brain-like computation, we talk about sparking neural network. Sparking neural networks are the third generation of artificial neural networks. And so far, there are more biologically plausible because they follow brain rules in terms of neuron behavior and also learning mechanism. They are event-based in terms of learning. And also they are very energy efficient, hardware friendly, because they work based on zeros and one, and the information that they receive and propagates are in terms of sparks, which is 0 and 1. And as you know, it is very easily compatible with the different type of hardwares, not just the traditional hardwares like von Neumann architecture, but also the neuromorphic hardware. And also they are a good candidate for quantum computing because they follow similar logic in terms of using digital information, zeros and ones. So we talked about advantages of this very new and very exciting neural network. But what is the disadvantage of using a sparking neural network? Currently, they are low in accuracy because they use just events. They don't use the analog information or the complete information that a signal carries. They just use zeros and ones that represents the presence of event or not. The components of a sparking neural network that you can hear in all type of neural network is they receive input as a spark trains. A spark trains, it means that the input need to be converted to a series of ones and zeros. They have a specific neuron model. The neuron model that are used in the sparking neural network are Leaky Integrate-and-Fire neuron model, which is the widely used neuron model due to its simplicity and less complexity for computation. Another biologically plausible is the Izekevich neuron model that can mimic a human brain neuron response to different stimuli. And also we have Hodgkin-Huxley model, which is very complex in terms of computation, but it is a kind of exact computation model that mimics real neuron. The other neuron model that I mentioned, they are simplified version of Hodgkin, Huxley model. The learning rule, mostly for the sparking neural network, it is a spark time dependent plasticity. It is a kind of Hebbian rule that we will dive in later on. But the most important thing about this learning is that beside a speciality, it can capture temporality in the data as well. So it is a very biologically plausible. It resembles the same behavior happens in the brain in terms of learning, but this learning is an unsupervised learning, and it happens in a real biological brain as a local learning. And we have different type of learning, reinforcement learning and teacher-based learning that you can see some of those variants in a convolutional neural network. So in a human brain, we have neurons that they are connected through axons, and we call these axons synaptic connection. These neurons propagate information in terms of sparks, electrical sparks. A sparking neural network, as I mentioned before, requires an input in way of a spark train. For that, we need to have an encoder to convert the analog signal to zeros and ones to be suitable for a spark neural network. In the architecture of a spark neural network, we have neuron model and also the connectivity. So you can use different topology to connect your neuron. You can use feed-forward topology to connect your networks, or you can use different, more biologically plausible way of creating a reservoir network, like a small world connectivity. And also the most important part besides neuron model is the heavy end learning, as we talk about, is spark timing dependent plasticity, or for short SDP. This part is unsupervised learning, so it can change the weight based on the event. Afterwards, you may need to attach a classifier or regressor to your model to be able to explain or to classify the information that the network provides. So the network helps you to identify the patterns between different train of sparks as input. But later on, you need to interpret those patterns. And from the output of the output neuron, you can extract the behavior of neuron in terms of spark rates, or in terms of, again, spark train. And you can try to use different strategy. The simple one is using a KNN model or any classifier to classify those patterns. And we have different biologically, again, inspired methods to classify the result of this specific learning algorithm. So let's look at the first part, the encoder. We have a lot of encoder. Bennett-Parker algorithm, event address event represent algorithm. We have a window threshold algorithm, and a lot of algorithm that you can use to change your input signal to spark trains. But I choose Bennett-Parker algorithm because this specific encoding algorithm is very powerful in terms of having different filter to capture the behavior of the original signal, and it is less sensitive to the noises in the signal. This algorithm is used to encoding continuous signal into spark train. And the steps of this algorithm is first to normalize the original signal, and also have a filter. The filter is mostly infinite response filter, and it has a sliding window that slides over the signal, so that the error between that specific window and the signal can be calculated. If the error based on the filter is below a certain threshold, the signal will generate spark, and afterwards, to avoid regenerating multiple sparks, signal uses the second error to calculate to avoid actually generating multiple spark for same features. So this specific algorithm, we will look into the implementation design, helps you to transfer your input to a spark train which is suitable for a neural network. We have a kind of visualization. You can see this is a signal. It is one channel of an EEG data. And after I applied Ben Spiker algorithm, it creates a spark train for me. You can see there are events as ones and you are having events as zeros. For us, ones are important because they carry information. So again, let's back to the architecture. The next component that is important for us to get ourselves familiar with is neuron model. As I mentioned before, we have different neuron model developed for sparking neural network, or actually the first purpose for developing such a model was to make a computational model to observe and understand human biological neuron. And Leaky Integrate-and-Fire model is the simplest one, which balance between the kind of performance and biologically plausible and resemblance to real human brain. LIF integrates incoming signals, input current over time, in a parallel circuit of capacitor and resistor. When the accumulated voltage exceeds a certain threshold, the neuron fires a response or fires a spark. After firing, the threshold, the voltage drops to a certain value that we say is a resting value for us, resting voltage. And there is a specific time, we call it refractory time, that although a neuron can receive a stimuli, the neuron won't produce any or fire any sparks. This is a refractory time that neuron requires to be able to respond to the next stimuli. The leaky part refers to the gradual decay of voltage over time. So this part mimics the natural behavior of electrical charge in biological neurons. This slide shows the circuitry of a LIF neuron model. And also you can see the, you can see the formula that help us to implement LIF model for our sparking neural network. As I mentioned before, in biology, a neuron receives a stimuli and it has a membrane potential. Membrane potential is the energy that is over time accumulated by different stimuli inside that neuron. If that membrane potential reaches a certain voltage, it releases a spark. When the neuron doesn't receive any information, the neuron is in resting state. It has a rest voltage. And after neuron releases a spark, there is a time, we call it a refractory time, that a neuron, even though it receives sparks or stimuli, it won't release or propagate information. If we go back again to this slide, the next component that we need to talk about is Hebbian learning mechanism. And from that learning mechanism, we mean spark time dependent plasticity. This learning behavior captures both spatiality and temporality in the data exactly the same way that human brain does. Spark time dependent plasticity receives data, changes the weight based on the information that each neuron receives. So it has two different kind of behavior: long-term potentiation. And in long-term potentiation, if a presynaptic neuron, let's go to this slide. If the presynaptic neuron sparks before postsynaptic neuron propagates information, so this is the time component that STDP can capture. So if presynaptic neuron sparks before postsynaptic neuron, the long-term potentiation happens. It means that the synaptic connection between these two neurons will be strengthened. Long-term depression means that the presynaptic neuron didn't fire in time, and the postsynaptic neuron propagates information. It means that there should be some error in the network. So without receiving any response, the postsynaptic neuron release or propagate information. So long-term depression makes sure that this behavior won't repeat in future by decreasing the synaptic weight and on the synaptic connection. This slide provides us with a visual presentation of the spark time-dependent plasticity. As I mentioned before, and I showed you in the previous slide, if presynaptic neuron sparks before postsynaptic neuron, a long-term potentiation happens. If the otherwise happens, the long-term depression occurs, and the weight can be updated based on this behavior, capturing the temporality of sparking behavior of neurons. So now that we understand different components of sparking neural network, how we are going to implement or simulate a simple sparking neural network. First, you need to define neurons and synapses. I mean, first you need to create network connectivity and also assign a specific neuron model. It can be LIF, Izekevich, neuron response model, or any other neuron model that it is designed and proper for using in a sparking neural network. Then you can set up the connectivity. In a very simple connectivity, you can use excitatory connection. We also have inhibitory connection. Inhibitory connection means that if a neuron receives sparks from a postsynaptic neuron, presynaptic neuron, if that presynaptic neuron is an inhibitory neuron, it makes the postsynaptic neuron inhibited or it makes the postsynaptic neuron not releasing an information or propagating information. There are different types of mechanisms to implement such a behavior. A simple one is that you assign a kind of negative weight, so that you make sure that the network won't excite the postsynaptic neuron to release information. So let's just consider excitatory networks. You just connect neurons in a way to create like a simple feed-forward network. And afterwards, you need to have an input signal. So in a real-life application, we use a sparking neural network to process data like EEG data, electroencephalography data that captured from human brain activity for the purpose of kind of biomedical applications. We can also have IoT device signals, device that captured from different IoT sensors, and also any other type of streaming data or time series data can be fed into the Spark neural network. But as we discussed it before, a Spark neural network cannot handle, or by intention, they don't handle analog signal. They use event as zeros and one to process the information. So you need to have a mechanism to change the analog signal to a spark train. As we mentioned it before, and we see in this presentation, we can use different encoding algorithm like Bennett-Parker algorithm and other type of encoders. Then you need to simulate neurons or the network for some time steps. And after that, you can transfer the implementation using some of those SDK to a hardware, neuromorphic hardware, to simulate that learning behavior on hardware, like a Spinnaker, Lohi, and so on. In the next part of our presentation, I'll invite you to my Google Colab so we can see implementation of Leaky Integrate-and-Fire neuron model. We also have implementation of Bennett-Parker algorithm. Also, I implement spark time dependent plasticity to show you this behavior we saw here in this plot, the long-term potentiation and long-term depression. And also at the end, we will put all those components together to train and visualize the response of a model in a simple sparking neural network. So the next step will be when you have this algorithm implemented in a software environment, you can choose a platform like Spinnaker or Intel Lohi to transfer your algorithm to simulate a hardware. Some of them require their dedicated framework like a Spinnaker. And sometimes you can use this PyNN API to communicate with the hardware. So let's stop sharing this slide. And go to the Google Colab. So I will again share. Can everybody see my Google Colab? Okay, good. So let's continue the rest of workshop here. I personally prefer to first understand the implementation of neural network from scratch, so that if I want to have a customized network, I have a much more room and flexibility to implement my own idea. So I start this workshop by running you through a code from scratch. Then I'll show you using Brian 2 framework to kind of implement similar network in that framework. This implementation is using PyTorch. Why I use PyTorch? Can we use Python without using Python arrays instead of using PyTorch tensor or TensorFlow? Yes, we can. But as I mentioned before, remember that this application are designed to run and implement on massive and parallel computational processor. So PyTorch provides a kind of framework to easily use GPU power. If you are not going to use a neuromorphic hardware and you want to use a von Neumann architecture, PyTorch provides you with this capability to parallelize the algorithm, the training algorithm, on a multiple GPU or even multiple instances like clusters. So let's again have an overview. Remember that we are going to have an encoding algorithm, which I introduced BSA. It is the favorite one for me. As I mentioned before, it is less sensitive to noises, and it provides you with different filters so that you can adjust the filter according to the input data. So let me first, before we jump to the implementation, I give you an idea about what do I mean by input data. During my research, I used different type of data for classifying and predicting neurodegenerative disease, like different type of dementia, Alzheimer dementia, frontotemporal dementia, and other type of dementia, or mild cognitive impairment. So with this application, so the application is to predicting or classifying different type of a certain disease. For this certain disease, we have different type of data. We have EEG data. EEG data are time series. We have fMRI data. They are in terms of images, voxels in terms of time steps or time points. We have PET scan data. We have clinical data. So for a sparking neural network, if I want to use different kind of data, I need to understand the nature of data and be able to design a proper design a proper mechanism or thresholding or a filter to capture the behavior of the data. Sometimes you have designed, you use a predefined filter, but you see that there is not enough spike created in the output signal, the spike train. So you go back to your code, change those hyperparameters, and try to run your code again. And you, as a developer or researcher, when you are working with data, or if you are working as a data scientist, you need to research and you need to dig in this process in a way that you adjust those parameters to have the best result. So sometimes, because we mentioned this disadvantage of sparking neural network, sometimes some students or some of my colleagues, they tell me that they couldn't get a good accuracy using a sparking neural network. The first thing that I suggest is that look at the hyperparameter and try to adjust it in a way that the output is spark train from encoder gives you kind of behavior resemble to the original signal, because we want to capture events. By that explanation, let's look at Ben Sparker algorithm. In the Benespeicher algorithm, as I mentioned to you, there are different steps. We normalize the signal. We define different filter. Those filter are finite response filter, and you can have it for short, long, and rapid kind of behavior. So you can, based on the information that you are trying to encode, you can use a specific filter, or you can design your own filter if the tree version of these filters doesn't satisfy your need. And after that, we have an error calculation mechanism. And based on that, this algorithm tries to create a spikes that is resemble to the original signal and avoids to generate sparks for the same feature. From Torch library, we import Torch functional, and we use matplotlib and also NumPy to use NumPy array for our calculation, for visualization. I define the BSA encoding algorithm by receiving this argument and input data. The input data can be a time series data, any time series event, IoT device input, sensory input data, EEG data, or if you have images, you need to think of this information as a time series. So in our application, for us, those images were static, as you can see. Those images were static data. But from one patient, we have multiple images captured in different times. So we use those image data in a time series fashion. But remember, if you want to use a sparking neural network, you need to have a kind of time series information. Another application that I can mention is video streaming. Consider that the job is processing a video surveillance footage. And in the video surveillance footage, if you look at or faced with this kind of application, you see that for a lot of time there is no event happening. Consider the application is human intrusion detection, or any kind of abnormal activity. So it means that for a normal situation, we won't see any specific event. But once a human enters into the scene, there should be an event generated to say that this is a kind of abnormal situation for your learning algorithm. So if you have different video frame, you can, using this sparking algorithm or this encoder, you can encode this information to events. If there is a movement based on the application, if there is a kind of changes in sensory data, for example, consider that you have a sensor that collects data and from temperature data, and it is for safety of a device, and you can see sudden rise in the temperature, so it is another event. These are applications that I want to introduce to you in a way that you have some imagination of why we are using this encoder and why we are using sparking neural network. So always consider the application is better to be a time series data, or as we say, longitudinal data. The algorithm you can receive, you can send a filter type. As I mentioned, we can design a filter to capture short behavior, short sparking behavior. We can capture long sparking behavior, or we can capture rapid spark behavior in the input stream. And we can go on with the implementation. The length of filter is a parameter that can be used in the windowing mechanism that we use to look at the signal. So basically, we define a window, and we input the sample data, and we slide the input over the data and apply the filter, then calculate the error. And based on the error, we calculate the spark train. We will have a threshold based on the calculating error here. We have a threshold that allows us to generate a spark. So when we are calculating the BSA encoding, from the length of the filter, we try to slide the window over the signal, calculate error 1, calculate error 2, and based on the threshold that we set, we try to generate sparks. In this way, by these two error mechanisms, we make sure that there is no duplicated of signal spark for similar event. And for the purpose of testing this Ben-Sparker algorithm, I generate two Poisson Poisson distributed signal, so that we can see these two signal using the BSA algorithm can be turned into a spark train. Let's run this a specific cell to see the result. So the component that I had here is an encoding function, BSA encoding function. I have a function to generate the 2D Poisson signal, and also I plot the result to show you the difference between the input signal and the output signal. First, I will generate the Poisson 100 timestamp and with a rate of 10. And then I call a spark train encoding algorithm. I give filter type 1, and I set threshold to 0.1. You can play with this hyperparameter, and instead of this Poisson signal, you can use a real value like EEG signal. And you can see the behavior. So this is the original Poisson signal. You can see that for the event, there are a spark created. Here, there wasn't a threshold, so a spark didn't generate here. And you can see there are too many sparks for this specific filter and hyperparameter. Let's change it to see. Consider that I want first to change this hyperparameter. I want to change the threshold, increase the threshold by 0.5. So remember this behavior, too many sparks. Basically, every time that there was a change in the signal, we had a spark. You can see now by increasing the threshold, I capture less event. Why that is important? Consider that you have an EEG signal, or this is a signal that represents some IoT devices. You know that these devices are prone to capturing noises. So if you use a very low threshold, you possibly capture those noises as an event. So again, when you have an application, please look at the data and try to play with this hyperparameter to choose it in a way that it represents the data. Avoid capturing noises, or in some cases, if you set the threshold too high, you possibly miss the real event in your data to be captured. Let's change to another type. You can see the behavior of the output spike changed in compared to the previous spark. So again, you need to analyze your input signal to see which one resembles the behavior that you want to capture. If you want to capture a specific event and you want to reduce the noise, set the threshold to a higher value. If you have a a signal carrying a lot of information, you may need to reduce the threshold to a proper value. But again, this analysis in the input data requires some knowledge in the field. If you don't have that knowledge in the field, you may need to uh, kind of consult with another person. For example, in our application, when we wanted to design these filters, we work closely with neuroscientists so that we could capture the event that a physician or a neuroscientist can, as a human, identify in a signal when they look at the EEG signal of a Alzheimer's disease person or any other kind of dementia or any kind of disease. So if we want again to go through the code, for designing the code, the filter is important, the type of filter. You can design your own type of filter. Then you loop over the signal, and by a windowing mechanism, calculate errors. And based on these errors, you can generate a spike or zeros. Remember to adjust the hyperparameters according to your input data, and always visualize your output to make sure that it is what you want. As a machine learning and AI scientist, I always use visualization for explainability to make sure that the behavior of my model suits the outcome that I expected. The neuron model. We talked about different type of neuron model, Izekevich and neuron response model and LIF. LIF is widely used because it is very simple in terms of implementation, and also it mimics the behavior of biology in less complex manner. And it is a best fit for a sparking neural network. Remember, as a machine learning and data scientist, you don't want exactly implement the behavior of the a kind of biological neuron or any other natural phenomena. When we are creating a computational model, mostly we get inspiration. We don't exactly mimic the behavior. Why? It is for the sake of computation. because of limitation of computational resources and the complexity in developing those models. So as we mentioned, Leaky Integrate-and-Fire is a simple capacitor resistor circuit that accumulates information over time, or accumulates the current over time. It increases in terms of biology, we call it action potential. In terms of membrane potential, when membrane potential reaches a certain threshold, it releases a spike, and after that the membrane potential resets to a certain value. You can simply reset the value to 0, but biologically the reset potential is, I think, minus 20, sorry. So let's look at, again, I use Torch to implement. Torch tensor is easily to use in parallel computing. If you want to use this as a distributed computing or parallel computing, Torch provides you with a very simple mechanism without changing your code to be able to spawn it on multiple GPU or multiple instance to have a better result. Maybe with this simple code, it is not very obvious. Why should I mention this? But consider that you are implementing a network of 1,000 neurons, and you want to fed like 100 time points for an EEG input. An EEG input can be a matrix of 14 channels, and consider like 200 time points or something like that. It is very, very simple, and consider that you have this EEG data for like 100 or maybe 200 patients. It requires a huge resource to calculate and process those information. So with the CPU, it is like a very kind of time-consuming job. But if you use GPU, you can train and see the result of your model within maybe hours. So it is important to know the kind of capability of these Python libraries to be able to use it. With the LIF, I created these LIF neuron classes. These are the parameters that LIF neuron uses, and you can easily refer to the. Can you see my slide? Okay, if you can't, you can easily refer to the slide that I provide with the mathematical formulation of a sparking neural network. So for the Leaky Integrate-and-Fire, so you can see that there is a membrane time constant. It is in milliseconds. We call it tau. And we have a reset voltage. As I said, it is the time after a neuron receives a spark, releases a spark, it drops the membrane potential to a reset voltage. For simplicity, we set the reset voltage to zeros. And for the computational purposes, because we are not always trying to mimic a human real biological neuron, we are using this sparking neural network to calculate real world applications. So it is not always to using this kind of implementation to investigate biological neuronal activity. If it is for the purpose of computation, you keep it simple. We can set a threshold. This threshold is for firing behavior based on the, again, application. You can set this threshold to a fix, or you can dynamically update this threshold within your learning algorithm. One mechanism that I like always to use is avoid fixed kind of value for certain things like threshold. So that threshold can be learned. If you put a fixed threshold and you don't know the best parameter setting for your application, it may require a lot of experiment to run and find the best setting. For example, if it is a classification task or any other machine learning task. But if you design a mechanism that this threshold dynamically adjusts within your network while the network is learning the input temporality and speciality in your input data, it can be beneficial in terms of less kind of human intervention and less parameter to adjust. You know that when we try to evaluate an algorithm, we look at how many parameter a user require to adjust. So for some certain parameter, if you can make it dynamically adjust in a self-organized manner, it can benefit your implementation and your application a lot. And we have timestamp here. We can set it to timestamp here. We can set it to as much as we want to run the simulation, maybe like 10 milliseconds and or maybe 20 milliseconds. We mention it in terms of millisecond because this is the way that human brain process data. The human brain process data in milliseconds or in nanoseconds, but it is much more kind of biologically plausible. But if your real-time application, you have data, time series data collected, for example, for days. So you're not the time steps or the time points that you are using, definitely it wouldn't be in millisecond or even nanosecond. It can be days or it can be, I don't know, weeks. It's based on the application. So we will have a function to reset the membrane potential value. Let's look at the function that simulates the neuron behavior. We implement the neuron is a Leaky Integrate-and-Fire formula here. And in each time step that it represents in the data, we try to calculate the neuron behavior in terms of generating a spike. My simulation steps are 100, and from this 100, each step is 1. So I will end up having 1 time points for my simulation. I create an instance from the class LIF here. And I create a constant current. And also I create a kind of non-constant current to show the difference between these responses for the sake of comparison. So let's start simulating and look at 2 different kind of input current. One current is a constant current. The other is a varying current over times. So we can see by implementing a Leaky Integrate-and-Fire neuron model, the neuron response should be in which way. So you can see I provided a current input, a constant current input, and I had spikes at time points 20, then a reset in membrane potential happens. Again, a spike, reset in membrane potential, and again a spike. The varying current input, you can see the behavior changes. We don't have this nicely kind of time interval in a spike. This happens in more real-time, in a real-world application. So you won't have a constant current. In real-world application, you will have a varying current input that can create different membrane potential behavior. When the membrane potential reaches a threshold, a spike will be released. Then the membrane potential will decay to a resting value. As I mentioned before, the resting value here for us is 0. In a real neuron, we can add, if we want to kind of implement a real neuron behavior, we can add a refractory time. So there will be a time that even though there is a kind of a stimuli, input stimuli, the neuron won't fire any spike because of the refractory time. You can use that refractory time or you can, avoid using it. It's based on, again, your implementation. If you think that it can help you to capture the pattern in the input data, you can add it to this implementation, or you can just remove it from your implementation. So again, when we are using the neuron model, make sure that the behavior, the output behavior in the development phase is what you expect from the input signal. So you can see if there is a spike, a frequent spike, we expect that neuron fires. Another biological concept here is that if just one spark enters or receives by a presynaptic neuron, it won't just jump to propagating a spark. It requires this information frequently in the time comes to the input neuron, so that it increases the membrane potential by accumulating those information. When the certain threshold is reached, the neuron will emit a spike. This behavior helps us to capture a repetitive pattern. So another advantage of this behavior is that we can let the neuron cancel the noises in the data. If, for example, in your encoding algorithm, you generate some a spark, but this spark is a noise. This behavior neuron model help us to cancel those noise if it doesn't appear in the later samples. So it can be considered as a noise, and the neuron won't propagate that noisy information to the post-synaptic neuron connected to itself. So let's look at spark time dependent plasticity. Spark time dependent plasticity, as we mentioned before, it provides a mechanism to change the weight between presynaptic and postsynaptic neuron. Consider two neurons are connected to each other through a synaptic connection. In this specific learning algorithm, lets us to capture temporality. By temporality, I mean the time that the information receives by the neuron. And also, if you provide a kind of neuronal topology by creating a specific, network connectivity, you can capture a speciality as well, like normal kind of artificial neural networks. So consider that these two neurons are connected to each other. If the presynaptic neuron sparks before postsynaptic neuron, it is a desired behavior. It means that presynaptic neuron propagates information to the postsynaptic neuron. We want this behavior to be encouraged. So what we do is increasing the weight, synaptic weight. But consider a scenario without the presynaptic neuron emitting or propagating information, the postsynaptic neuron fires sparks or propagates information. This means that there should be some fault in the system. What we do, we decrease the synaptic weight so that this behavior won't happen next time if this behavior was as a result an error. Let's jump to the code. For this code, we provide the parameter that it is defined in the spike time dependent plasticity formulation. You can see that we have constant for long-term potentiation. We have constant for long-term depression. Also, we have the weight change parameter, how much we want to change the weight in terms of long-term potentiation, and how much we want to change the weight in terms of long-term depression. And we have maximum synaptic weight and minimum synaptic weight. By minimum synaptic weight in the network, we mean that there is no connection between these two neurons. Because if you look at the formula for changing the weights, you see that in changing the weight input signal multiples by the weight. If the weight is 0, it means that there won't be any information propagating from presynaptic neuron to postsynaptic neuron. So what that means, it means that if we want to interpret it in a biological sense, we say that there is no connection between these two neurons. Although the connection from the kind of network connectivity presents, but if we set it to 0, it means that there won't be any communication channel between these two input. So it can again use as a way to organize your network connectivity. The maximum weight, you can set it to any number, but remember, if you set it to a higher number, longer time requires for training. And also, if the number, for example, here, max weight is very low, there is a high chance of saturation before network learns the pattern inside your data. So always be careful about setting this hyperparameter. Look at the size or scale of your network and look at the behavior of network. If you see saturation happens, you can increase the max weight. And also you can, for pruning mechanism, for removing the faulty or noisy information propagation, you can use this synaptic weight decreasing to 0 during your training phase, so that you can, if there is, for example, for some period of time, you don't see a specific neuronal activity between two neurons, you can decrease that synaptic weight to 0. So this connection will be removed. It means that, if you want to look at the data, it means that this connection wasn't necessary. So by this mechanism, gradually you will reduce the possibility of capturing noise if it happens. So let's look at the STDP function. For the STDP function, we will increase the weight if the long-term potentiation happens. If the neuron receive the presynaptic neuron emit a spike before postsynaptic neuron, and we will decrease the weight here if the postsynaptic neuron emit a spike before presynaptic neuron send any information to it. For this illustration, I provide a kind of I generated data from minus 50 millisecond to 50 millisecond to show you the behavior of long-term potentiation and also long-term depression. Let's run this STDP, a simple STDP function to show you the behavior of the STDP. You can see it's similar to the behavior that I showed you in the slide presentation. And it is a kind of neuronal behavior observed during the biological examination of neuron activity, receiving a stimuli. And you can see this part provides the upper part of the plot shows the long-term potentiation, and this part shows the long-term depression. So here on the upper part, we can see the time that the weights will increase, and the upper on the lower side, it shows the time that the weights will decrease according to STDP rule. So again, STDP rule captures both temporality because it works based on the time of arrival of a spike, and it governs this weight change behavior based on the mechanism of long-term potentiation and long-term depression. So let's put all these components together: the encoding algorithm, neuron model, and also the learning behavior to create a simple sparking neural network. For this purpose, I have 2 input neurons in the architecture. I have 10 hidden neurons fully connected to 2 input neurons, and I have 1 output neuron, again fully connected to the output neuron. And I use 2 different pulse-on signal A and signal B, to show you the behavior of a sparking neural network after learning this behavior through time. So let's again look at the theory. I have 2 signals. These signals have 100 time points or time steps. I encoded these signals into 100 zeros and ones. Different signal provides different spark train. Then I will have a architecture for my network: 2 input neuron, 10 hidden neuron, and 1 output neuron. I will run this STDP learning algorithm from the first time point to the last time point, and try to, based on these two input, try to change the weights of my network so that network can learn to differentiate between these two signals. Again, we learned those components before, so here we just put them together. Here we have the same function that uses BSA algorithm to encode the data. I use this function to generate Poisson tensor or two Poisson signals. You can, instead of this, use a real world application. You can use two signal from two sensory devices or any kind of information that you want. We have LIF neuron implementation here. And also, we have a class here that creates the topology of my network. In my class, I use input neurons, I used hidden neurons, I use output neurons. The number of my input neurons can be, I can change it to 2. Sorry for this. Well, let's just keep it for here 10, but you can change it. You can, okay, that's 2. Hopefully there is no error because I didn't test this one. I have hidden neurons, 10 hidden neurons. I have 1 output neuron, so it can create my architecture. For the weights between input neuron to hidden layer, I created these tensors, randomly assign weight to each synaptic connection. From the hidden neuron to output layer, I use this variable to create the random synaptic weights. I create a kind of learning rate for STDP so I can decay it while I'm training the model. This can be used to control the amount of weight decrease or increase. In the beginning of your simulation, you want to have kind of a higher or bigger step for increasing or decreasing the weight. When you are reaching to the end of simulation, you want to decrease it. So here I use the fixed learning rate, but it is a good practice to dynamically control it. As I mentioned, mostly we start with a bigger step at the beginning and we decrease it to a smaller step to give the chance to exploit the space, the problem space for the model to learn the behavior of the input information or input signals. So in the forward function, which is the learning function, I try to calculate the hidden inputs and the hidden sparks for my neuron. And afterwards, I calculate the information from the output layer by by multiplying the input and synaptic weight. And also here you can see that I multiply the spark with the weight and accumulate them. So in that way, each neuron in the hidden layer or in the output layer, based on the simulation time steps, learns and accumulates the information, and each neuron, based on this information, can emit a spark to the next layer. So we have a function to apply STDP to change the weights based on the sparks in the input data, and also based on the membrane potential. Remember, every neuron, they based on the membrane potential and based on the threshold, which here is fixed for all of the neuron, propagates sparks. The membrane potential at the beginning of the simulation is set randomly, but it changes when each neuron receives information and data. We can calculate a spark rate in a specific window to show the behavior in terms of the behavior of output model, and it is for the sake of comparison. You also can use it to feed it to a classifier or regressor. So again, remember, a spark time dependent plasticity is an unsupervised learning algorithm. It just changes the weights of your network, but it cannot help to classify or to regress the data, the final information. So you can attach a kind of classifier head or a regressor to your model to identify or to classify different behavior in your network. So let's try to run this simple network. So I have output neuron spark trained for signal A. You can see there is no spark for this specific signal. I have output neuron spark trained for signal B. You can see I could calculate a spark rate here. Here we calculate that spark rate. What is that? Okay, here. It can help us at the output neuron, help us to easily classify the input. And you can see here, these two signals are very kind of distinguishable. You cannot see this behavior in real world scenarios, but it won't be that obvious in terms of being different from each other. But it can give you some understanding that this behavior can be classified easily, either by using a spark rate or using a sophisticated algorithm like KNN, or I can introduce you another interesting algorithm. If you are familiar with self-organizing map algorithm, DESNN tries to, in a kind of time dependent manner, tries to classify the outcome of an output neuron based on the times that output neuron sparks to a classifier that in a kind of self-organizing way creates classes out of your input signal. Another type of supervised learning behavior that can incorporate STDP is rewarded modulated STDP. This a specific algorithm is using reinforcement learning to provide you a kind of capture both unsupervised and supervised kind of mechanism from biology and put it together so that your network, while applying the STDP kind of mechanism, which is a biological way of changing the weights in your network, use a kind of rewarded modulation to provide a reinforcement learning to classify the input based on the contribution of the input signal into the behavior of the output neuron. So far, we implement this algorithm from scratch. So if you look at the code and look at the paper or the formulation of Ben-Spiker algorithm, Leaky Integrate-and-Fire, and also STDP, you can easily see each mathematical component implemented here. Why I started this implementation? To help you to completely understand how to implement a sparking neural network from scratch. Also, it gives you some understanding and some flexibility if you want to use your own kind of design. Consider that you have a special topology for your network. You have a special way of capturing the spark rate. For example, here we just look at the whole a simulation time to calculate the spark rate. Consider that you want to implement it in a way that in a specific time window, look at the behavior of neuron and try to add more kind of learning mechanism using reinforcement learning to change the weight instead of waiting for simulation to end by STDP rules and try to propagate the error to the network. And remember, a sparking neural network, there are discrete networks, so derivation and backpropagation cannot be easily used in this type of network, but there are a lot of interesting research that incorporate this backpropagation behavior by using or applying this spike rate or spike behavior in time window so that it can propagate the error and adjust the weight that STDP already changed during the simulation. This part of the presentation uses Brian to create a simple network like what we discussed. Here it is much more sophisticated, but you can see if you are going to use a kind of framework like Brian, how you can implement a similar behavior. If you import all the library from Brian, you can use it to define a neuron model. Here we use this specific formula to create a LIF model for our simulation. And this is a kind of how can I say it? This is a kind of way that Brian framework define neuron model. Also, you can define STDP rule, and you can define any synaptic connection by providing a kind of a string. So let's start by, again, using a tau, and tau used for simulation time. Synaptic strength is used for as a weight for changing providing or producing a spark. We have a threshold for releasing a spark. So we define here, based on this equation, a simple LIF model. You can modify it or make it a little bit more sophisticated to look like a real LIF model with all those components. Here, I create with this function number of neurons, and I provide a threshold for them to fire. The threshold value we set is 8 here, and the rest voltage for membrane potential to decay after releasing a spark. Here you can see simply set it to 0. You can adjust this reset voltage to any number. Again, play with this hyperparameter according to your application. Try to adjust them based on observation. One main skill that I always tell my team member and students to learn is that always look at the problem like a scientist. When you are developing, you're not just a developer. If you are using these tools as a data scientist, machine learning, and AI scientist, you need to run different experiments, run different hyperparameter setting to make sure that your model learns the behavior of expected input and provide expected output. And then when you use it in inference mode, inference stage, your model is behaving according to what you experiment, what you explore during the implementation phase. And always remember to monitor your model and provide some feedback to your input model to incrementally or in some time interval refine the or adjust the learning behavior. You may need to change the parameter, you may need to even add layers to your network, or you may need to add mechanism to skip some layer, and all those things happens when you put your network in application, in inference or in production. So we create a group of neuron here. The group of neuron are 8 neuron. Initialize those membrane potential randomly. You can see the syntax here is using some string, and it is the syntax that Brian uses. And after that, using synapses. Synapses function creates connectivity between this graph of network that we create here. By putting probability to 0.2, you say that out of these 8 neuron, the connection connect randomly 20% of this neuron together. So you will have a sparse network here. It is not a fully connected. You can change this probability to 1 and have a fully connected network. We can use a spark monitor to record a sparking behavior of the network. And also, we can create a network with all those components, a spark monitor, a spark state, and the graph and synapses. Again, look here, we have the graph setting, and we have a synapses here. Let's run this simulation to see if this network creates similar behavior for us in terms of providing a spike and also showing us the membrane potential for all those neurons. Remember, we have just 8 neurons here. Oh, okay, let me see, what did I change? Okay, I think I changed something here. Okay. Okay. Uh, you can see that it couldn't detect the Brian library. So make sure before you use the code, you install the library. I thought that I already installed it. So you can easily pip install Brian. And upon successful installation, we can run this part of the code. It takes a little bit of time. It is because I didn't use a very powerful machine in my Google Colab, but anyhow, it's like providing result for us in a few seconds. So how many neurons? It was just 5. Okay. So because I had a very few number of neuron here, just 5, and also I create 20% of connectivity, this behavior was expected. Just this plot shows the index for the neuron that spark in time 0, because we provide this simulation from minus 0.04 to 0.04 here. And you can see the changes in the membrane potential for all those neurons during these 2000 time points. And how these 2000 time points come here, you can change it and you can get a different result. So let's increase this to maybe 14 neurons. I hope that doesn't take too much time. So at the end, we saw implementation of sparking neural network, a complete sparking neural network. So if you want to take it from this workshop, by the end of this kind of tutorial, you should be able to create a sparking neural network. If you want to create a much more sophisticated, these different steps should help you easily to create a much more complex sparking neural network. BSA can help you to convert any type of data, time series, analog data to Spark train. And also you can apply STDP to create the or adjust the weight during the training. And you can see in this result, by increasing the number of neuron here, I have more neuron during this simulation time emit a spark. And also here shows the changes in the neuron membrane potential. You can see they start from 1 or something like 1.70, and after they release the spark, they decay to 0 or reset voltage for membrane potential. So let's again recap what we've gone through. We learned a whole component of sparking neural network from encoder, neuron model, learning algorithm. You can put all these components together to create a full sparking neural network. And also remember here in this part that I use a kind of a sparking neural network from encoding to training and observing the output. I use the spark rate to differentiate between these different input signal. So you can use different mechanism. Still, this spark rate, calculating a spark rate can help you, but it is not very sophisticated. You can apply another classifier on top of this. Remember to look at the papers and books related to sparking neural network to learn more exciting and sophisticated algorithm. And also, if you don't want to use this code to implement from scratch, you can use libraries like Brian and PyNN to create your network. And afterwards, when you create your network and you in the simulation, you made sure that the behavior is expected as what you wanted. You can use the neuromorphic SDKs like Spinnaker and NX SDK to move the algorithm to a neuromorphic hardware. So here, by wrapping up all the presentation, I can say that the workshop is finished, and I will look forward to receiving your question and answer them. Thank you for your attention and presenting this workshop.
Thank you so much, Dr. Bahrami, for introducing us to this fascinating aspect of technology. It was an incredible session, and I am sure that our participants enjoyed the workshop as much as we did.
Yes, it truly was a wonderful workshop. We really enjoyed it.
Thank you very much. Thank you, the organizer, and thank you all your attendees and students. I hope you
Before,
learn.
before we wrap up, we did like to present you with a token of our appreciation for sharing your expertise with us today.
That's lovely. Thank you very much.
Your expertise on neuromorphic computing and spiking neural networks has truly inspired us, opening doors to new ways of thinking. We are excited to take that we have learned and push forward in our own journeys.
Thank you
Thank
once again for your time, wisdom, and dedication to advancing this field. We are incredibly grateful.
Thank you very much. Thank you. It was a great honor and pleasure to be here and share my knowledge with you.
Now it's time for a quiz. We have prepared a few exciting questions based on today's session. Make sure to participate and test your knowledge.
You can submit your answers using the link provided in the chat box. It's a great way to recap what you have learned today.
Good luck everyone. Let's see how well you have absorbed the key points from the session.
And also stay connected for other track updates on our WhatsApp group and do visit our Instagram and YouTube pages as well.
Thank you for being such a great audience. We wish you all the best for your upcoming endeavor and hope to see you in our next session navigating the future autonomous vehicles at Epsilon 2024. Thank you.
Thank you very much.